So I guess we're going. So now we know. He's gonna visit the group. I think not really sure. Maybe didn't know this. You guys didn't know he's visiting until the 21st. He's gonna tell us about a result which I think is awesome result. It's how to solve this problem called the evaluation problem in logspace, essentially. Yeah, we really love it. So,
thank you, Bruno.
please go ahead.
Thanks for the introduction. Well, okay, essentially he's doing a lot of work in that sentence. But yeah, I'm here to tell you today about this problem called the tree evaluation problem, why you should care about it, what's the context, why do we think it's hard, what are the challenges to that hardness, and how have those challenges been realized in the last couple of years. And at the end of it, I'll get to some work that's soon to be published, which Bruno just talked about. But for starters, I'm going to introduce the problem, and I want to tell you why this is a problem. Okay, so tree evaluation is parameterized by two parameters. So the parameters are an alphabet size k and a height h. And the problem is just that you're given a full binary tree of height h. And the leaves are going to take values in this alphabet size. Just think of it as the set 1 to k. And then in the interior nodes, as part of the input, we're going to specify an entire function, which takes in two elements from k and spits out an element of k. So the way you compute this thing is in the natural way. You start at the leaves, you use them to compute the level up, then you use those to compute the level up, and you go all the way to the top. And at the top, you'll spit out some number k, and that will be the output of the function. And of course, you can think of decision variance. Is this equal to k? Is it even odd? Et cetera, et cetera, et cetera. But this is the general structure of tree evaluation. And so I said that the internal nodes have to come as part of the input. So just to kind of specify in advance, the input side to the problem n, this is going to be like, well, the height, the tree has 2 to the h, say -1 internal nodes. And for each of them, I have to write the entire truth table. So it's case for log k bits to write the entire truth table. And of course, there's like plus 2 to the h times log k there, but this factor is dominated. The important thing to know here is that h is like logarithmic, and n can be up to logarithmic in n, and k can be up to polynomial in n. Pretty much no matter how you set the parameters, that's the ceiling for both of those. So that's what we're working against, and I'm just going to then write log n, which is the quantity we're going to care about for pretty much the entire lecture. This thing is, think of it as like h plus log k. So if I'm shooting for logarithmic anything, this is the number I'm shooting for. All right, and what do I mean that we're shooting for logarithmic? And again, why do we care about this problem? Let me quickly survey the landscape of complexity classes that we're going to be talking about today. So the big one, the top one for our purposes is P, polynomial time. So we're dealing with a regime where everything is very small. We're not above P, no NP, etc. We're down here. The top class we're going to be dealing with is P, polynomial time. And the smallest class we care about is NC1. And NC1 is the set of all log depth fanning to circuits. Has many other definitions, but think of it as actually kind of like this, but over the over 0 and 1. So log depth formulas, and then in between, we're gonna have a couple classes. We've got NC2, which is the same thing but with log squared depth, polynomial size, and then we have space bounded classes like log space, Turing machines where the work tape is logarithmically bounded, and L, the non-deterministic variant of it. And of course, there's a whole tangle of classes existing on each of these lines, but these are the big ones for today. So where does tree evaluation fit into this? Well, it's pretty clear that you can compute Like NC1 reduces to this because again, if I just set k equals 2, I can encode any NC1 circuit as an instance of tree evaluation. What's the upper bound? We know it's in NC. We know it's in NC2. We actually know better than that. Again, somewhere along this line. But this is basically the best of our knowledge. And tree evaluation is going to be our sort of antagonist for the day, and our protagonist is going to be log space. So we're talking about what is the space complexity of tree evaluation. It's going to be the focus. So why do we care about the space complexity of tree evaluation? Why is this a question worth studying? Well, the reason that tree evaluation was introduced in the first place, it's come under many different names with different sizes of parameters, but for today, this definition that I said over here is due to Cook. Okay, I need to get the order of objects right. It's for the word. Cook, Mackenzie, Ware, Braverman, and Sanford. Very not alphabetical. But so they introduced this tree evaluation problem, and they said, okay, look, this problem is obviously in P. You know, you just do the algorithm that I described earlier, like the definition of the problem, start from the bottom, compute your way up to the top. Obviously in P, but their conjecture is that the space required for tree evaluation, let's say, I just want to fit it inside the boundaries. Okay, requires space h times log k. So remember, h plus log k is our log space algorithm. They conjecture that it takes h times log k space. In other words, they introduced this problem as a candidate for separating polynomial time from logarithmic space. And we're going to get to, well, okay, why don't I just say why this is. So what is a better, what better space bounded algorithm do we have than the one I described? Start at the bottom, compute your way up. Well, there's a natural one. You know, you can reuse space that's used for older computations. These things are only relevant for a certain period of time. So when you kind of distill this down to its essence and you come up with the best version of it, you get what's called the pebbling algorithm. And the pebbling algorithm is a very simple thing. For each node, or for node in question, compute the left child of V, call it VL, save the answer, and compute the right child of V. So this is our inductive procedure. You start at the top, I'm going to compute this node, I'm going to save the answer, and I'm going to compute this node. How do I actually compute these things? Well, I'm going to compute the left, and I'm going to save it, and I'm going to compute the right. And what's the space that this takes? Well, it's going to be, at the top, it's going to be the space required to compute the left, plus the space required to save this answer, plus the space to compute the right. Well, sorry, it's the maximum of those two. Space to compute the left, then you erase all of it except for the answer, and then you do the space to compute the right. And, well, what is the difficulty of this? Well, this thing is of height 1 less, so it's going to be, again, the max of the space to compute the left, and the space to compute the right while remembering the left. And you just work your way down the tree, and of course, at each level, I'm remembering one element, log k bits. And I have to do h minus 1. Of course, at the bottom, I just kind of get the answer. Because h minus 1 times log k. That's what the pebbling algorithm gives you. And I call it the pebbling algorithm because their conjecture of the lower bound goes via a pebbling argument. And a pebbling argument says that essentially, this is the best you can do in a naive sense. If you want to actually, if at any node you want to be able to compute it, you can play this what's called a pebbling game, which is just arguing about like I have to know these two values to compute this one. And assuming all the space is independent, this is the best you're ever going to do.
Maybe it should be said that pebbling arguments,
Mhm.
they give you lower bounds on some kind of weak model. And for many years, people have been using these pebbling arguments as some kind of proxy to mean that if in the pebbling model it is hard, then it's probably hard for log space.
Yes, right.
And that proxy was a very valid way of thinking about space until essentially your paper
Sure.
appeared.
It pops up, these pebbling arguments pop up in a lot of places. For example, there's this alternate, we've got these proofs of work and whatnot in blockchain. And there is actually something called proofs of space. And there's even extensions therein. And a lot of it relies that the idea is you're supposed to prove that you've committed some amount of space in your hard drive to complete a problem. And pretty much all of them use pebbling. Like it's some function like a gen function or something, where the best you can do by all appearances is this pebbling algorithm right here. And that's a way to commit to having used a certain amount of space. So that's the conjecture of Cook et al. I will also say that besides having the pebbling algorithm or the pebbling arguments at their disposal, this problem has also appeared in a different setting of lower bounds. So I just want to mention that real quick. So you can think of a generalization where I allow not just fan in two, but like an arbitrary fan. And this has been studied in the literature before in the case where the alphabet size is fixed. There's a problem called the iterated multiplexer problem, which again is now parameterized by a fan in, called D, and a height H. And it's the same thing there, but fix K to be 2, and now all of your matrices, you're specifying an entire function on D bits. Okay?
Sorry, I'm not there.
Sure.
Can you repeat?
So, right, so IMX DH is now, you have fan in D, and each of these things is fan in D. And again, the height of this tree is H. And you can parameterize this by K, D, and H, but let's just treat the Boolean case for a moment. So this thing has a different set of parameters, and is now like, I don't know, D to the H. Yeah, it's roughly D to the H, or times 2 to the D, something like that. Doesn't matter. The point, actually, I guess I will write that. So the size of this thing in comparison to this is like, you've got D to the H nodes in your tree. You have D to the H minus 1. Your K is now 2, but you have to specify an entire function on D bits, so this is 2 to the D.
Okay, so you're saying now you have a tree, the height is still H.
Height is still H. I've changed the fan.
D, but now each wire carries a bit.
Each wire carries a bit. Again, if I generalize this, it would be like D to the H times K to the D, if I let you have all 3 parameters. But I don't want you to focus on the unbounded fanning case too much. We'll touch on it at the very end. I'm only introducing this to say that this problem is sort of the candidate example for separating P from NC1. This is a different, but even more long-standing line of work. And in particular, there is, running out of space. There is something called the KRW conjecture. Named for Kirschner, Raz, and Vigderson, which says that version, the iterated multiplexer version, requires.
There's a rather implied.
It implies it. It's a more specific conjecture about the structure of these things. But ultimately, if their specific conjecture is true, then what it implies is that this problem requires depth omega of D times H. And I just erased what n is, but this is once again like log squared. This thing is log squared, this thing is log squared. So the conjecture, the long-standing conjecture, is that this, when you generalize the fan, and this thing actually is hard for NC. So there's a long, this is all just to say that this is a long line of work showing that this particular problem exhibits some kind of hardness which appears all over the place. And really what that hardness is something called composition. The idea is just that I'm I have functions that are completely unrelated to each other, and so for whatever computation model I do, somehow whatever I do here or here, like nothing I do over here has anything to do with what I'm doing over here, and so this the complexities sum up in like a natural way. These are like direct sum theorems, is what they're typically called. And this is basically the most general example of it, because I'm allowed to plug in the hardest function, a random function here, anything I want. I don't have to worry about the complexities of these inner functions. The problem is that they're all scaled down logarithmically because I have to specify the whole truth table. But as long as I pick these very hard and completely unrelated functions, I would hope that the complexity scales with the height, and this is what puts us above logarithmic depth, space, etc. That's the general gist of where this line of work came out of. So is there any questions up to this point about the setup? Again, don't worry too much about iterated multiplexer. This is really the problem we're going to be focusing today, and don't worry about formula depth, we're talking about space. Okay, good. So then before we move on to what actually space looks like in this world, I want to mention that these direct sum theorems, while they're very natural, they do not always hold. And there's some very famous examples where they fail. So I just want to mention one. I'm not going to write it, but I just want to mention it in a casual sense. So imagine you're playing a game where you have a referee who picks 2 bits at random and sends the left bit, call it X, to you, and sends the right bit, Y, to your friend. And what's the game? You both have to decide independently, without talking to each other, after receiving the bits. You have to decide on a message. And the message is going to be of the form player, whoever, got 0 or 1 or something. This player got this bit. And you only win if you agree, if the message that both of you sends agrees and is true. Okay, so Bruno and I both get a bit. Bruno gets Y, I get X. And we can decide in advance on a strategy. But once we see the bit, now we have to come up with some way of answering this query so that we're consistent with each other and with the truth. This, since the bits are selected at random, there's like an easy half strategy.
Consistent, right? Because I could just say my bit is 1 and
consistent and true. So like if I say Bruno got a 1, Bruno had better have gotten a 1.
Right, but I can just say I got whatever I got, and
Yep.
you can say you can say I got whatever you got. It has to be the same player.
Yeah. So I can't say I got this and you say you got you got this. We have to say the same player and the same bit. So we both have to say Bruno got a 0. Something like that. Is that good?
Message has to be the same.
Say it again?
The message has to be the same.
Yeah, the message has to be exactly the same. And it has to be true. So saying Bruno got a 0 is about the best we can do, actually, right? Like you got a half strategy, and it's very easy to prove that you can do better than this. And in particular, if we play iterated rounds of this game, so we do this, and if we get it right, then we get to move on to the next round where the same thing happens, and then the same thing and same thing. Obviously, we start at a half probability of success. We go down to a quarter, having to play it twice, an eighth, and so on and so forth. This isn't quite a fair way of doing composition. The more fair way would be Bruno and I both get 2 bits. So Bruno gets Y1, Y2, I get X1, X2. And now we have to declare values for both of the games. So the first game is played on X1 and Y1, and the second one's played on X2 and Y2. And of course, these are independent bits. So by all appearances, there's nothing that you can do to improve, and you would get a quarter again. And of course, this fails. This is actually a case where you can still achieve a half probability of getting both games correct. So, Suhel, you probably know this one. It's not a hard strategy. Does anyone know this one?
So you just have to answer for both games.
Yeah, and you have to answer on X1 and Y1 for the first one, and then X2 and Y2 for the second one. But you get to see both of them when you send both of your answers.
Probably it's some strategy like correcting the beat. So they have to see the first games.
It's actually even more straightforward than that. So I'll just say it. So what am I gonna say? Let's say my bits are x1 and x2. So what am I gonna say? I'm gonna say that I got x1 in the first game, and Bruno got x1 in the second game. x1. I'm ignoring x2 completely. What does Bruno say? Bruno says, well, I got y2 in the first game, and I got y2 in the second game. Right? And this works exactly when x1 equals y2. So they're unrelated games, but it doesn't matter, right? Because we're answering consistent players, and as long as the bits are equal, we pass both games. Doesn't matter that we get both of them wrong, potentially, if the answer is false. So it turns out, of course, you can actually show that enough versions of this game played in parallel are your success probability goes down to 0. This is a parallel repetition game. It's not an easy theorem, and we barely know anything for these games. Like even when you move to 3 players, we only just barely know that it goes to 0. We don't know at what rate. We don't know practically.
So if you beat this game,
Mhm.
instead of having just
Two.
twice,
Yeah.
twice we did 3 again, probably 1.
No. As the number of instances you play goes to infinity, it exponentially decays, but it's a slower exponent. It's not the exponential you think. Because I mean, you can always get like 2 to the n over 2, where n is the number of rounds, just by playing the half strategy on both of them. It's even slower than that, but it is still exponentially slow. When you move to more players, all we know is that it goes to 0. We don't know what
we
it
know a
goes.
strategy better than n over 2.
I didn't know if we know a strategy better than an over 2 for this game. Parallel repetition luckily applies to all 2-player games, so that's nice. Anyway, but this is just to say that you have to be very careful when you're dealing with composed functions, because it's not at all obvious that direct sums hold. And in fact, it's so tricky that the exact game that I just said appeared in a published paper from 1987, and they just assumed that it decays exactly as 2 to the n. I think this was published at ToC. And it was only a couple years later that we figured out that it's not true. So, yeah, these are easy mistakes to make. But okay, so let's move back to what we actually care about, which is tree evaluation. Does hardness? Well, a lot of people, especially those in the orbit of Steve Cook, have worked on this problem over the years. And the original paper was this CMWES12, where they conjectured hardness. And they showed that this actually does hold for read once. No. Read once comes the error. They showed the full lower bound of h times log k for a model called thrifty branching programs. So first of all, is everyone okay with branching programs? Branching programs are just a syntactic model of space. And really, when I say space h log k, what I mean is exponential in that size branching programs. Because it just translates logarithmically. I'm going to try and stick to space wherever I can, but when I introduce these hardness results, I can use branching. So what's a thrifty branching program? It's a very specific restriction to tree evaluation. And it's as follows. If I take this node, for example, notice that there's exactly one relevant place. Most of the input to the tree evaluation problem is useless, right? And when I say most of it, I mean that there's log k bits in each node that are relevant. So there's only like 2 to the h times log k relevant bits in the entire function. And the rest of it is, places that will never be accessed. A thrifty branching program is one that indeed never queries an irrelevant spot in any node in the tree.
Right, so the relevant entry is the entry that comes from the wire.
Exactly. So this wire says a number, this wire says a number. You go to that place in the table, that's the only relevant spot. Everything else has no determination on the output. So it's natural to say, well, my branching program can't read these other spots then. What could they do with it? And if you make that seemingly innocuous assumption, you actually get the full lower bound on space. And in fact, this was extended even for non-deterministic branching programs. So even NL can't, NL, which only does thrifty reads, can't do it. So this is a pretty, this is, I think, why the problem gained a lot of traction at first, because then a couple of years later, the non-deterministic case was new. 2015. I should, yeah, 2012, I said that. And then it was also shown for read once from 2 programs. Originally, it was shown for read once branching programs by Iwana and Racal. It was 2015. And once again, even in the non-deterministic case, it was shown by Edmonds, Cook, Edmonds, Cook, Mendelbolini, and Tony Patasti. This was 2017. So people by 2017 were even getting hope that this could be used to show non-deterministic log space is not equal to P. And it seems like all of these are full lower bound. All of these get H log 10. And there was nothing in the way of direct upper bounds. There's a lot of internal notes this whole time that are passed around a whisper network of people who have been Steve Cook's master's student and thus forced to work on this problem for some particular period of time, myself included. And there was like a couple of upper bounds if you specify these nodes to be really well-structured functions, but nothing particularly interesting. There's also some results for the like height 3 case, for example. You know, there's only a couple of those. There's no serious upper bounds that came out before this period, but what we're going to talk about today is that there was a line of work which was seeming to challenge the big assumption about why this problem should be hard, even though it wasn't actually used to prove upper bounds on it. So what's the big assumption? The big assumption is that when I do the pebbling algorithm, I compute the left, and then I save that answer and compute the right, I'm assuming that I can't use the space that I was using to save the left node to help compute the right node. And why should you be able to use it? This is a completely unrelated node with no connection to this thing. So you're just remembering log k bits. How could that ever actually help you to compute an unrelated node? And it turns out that this is this kind of direct sum thing, which rests on an unfounded or a not solid basis. And that's what we're going to talk about today, up until the point where it actually was used to realize upper bounds against the tree evaluation problem. So, any questions?
So in the final algorithm, does that, I mean, you have a better space bound for evaluation, right?
Now we do this.
Is that a constantly resting function or?
No. It is right. So remember these thrifty and read once assumptions. The algorithms we're going to see are going to absolutely flaunt those restrictions. You're going to read every bit of the input a polynomial number of times. So yeah, including the irrelevant bits. But we'll get there when we get there. So that's the story thus far. Any questions? All right, let's see some proofs. So Barrington's theorem came out in the late 80s, late 80s, a while ago. And it was kind of a bolt from the blue. So Barrington's theorem was related to this class NC1 that we talked about earlier. And essentially, there was a version of the pebbling argument that operated in people's minds at that point, which is, yeah, you can do NC1 in like log space, you know, it's only a log depth thing. You remember one bit at every level. compute the left, compute the right, so you can do it in log space. But if you move to like the branching program world, what's the width of this thing? You know, how many bits you actually have to remember? It's probably exactly that. You have to remember like a lot of bits. And Barrington showed that in this, that's not true. Actually, in a very strong sense, that's not true. So we're going to see a proof of Barrington theorem, and I'm just going to state it in a different way. I'm going to sort of lie, but it's going to be morally correct, and we can talk about the actual parts later. But essentially, what he says is that morally, a log depth circuit can be computed with only 3 bits of memory. I'm going to put quotation marks here so no one takes this out of context. I mean, you need logarithmic memory to do all kinds of stuff like reductions and keep track of how long you run. But morally, the actual computation of the circuit only uses 3 bits of memory. So this is completely outside the realm of the penalty argument, right? Forget logarithmic, we just have 3. Now, okay, why do we even expect this? So intuitively, maybe the reason we could expect it is that if we're at some gate in the circuit, well, we have some value V1 and V2, let's say we're computing an AND gate. And whatever else we have to remember in the computation of the circuit, this is the only thing that's relevant at this exact moment. Somehow the local window is constant size. So maybe we could hope to get it, but of course we have to remember everything else that's going on in the circuit. If we just throw that out the window, then like, well, yeah, we can compute this gate, but then what are we going to do when we get higher up in the circuit? And what Barrington's theorem does is it kind of splits these 2 uses of space. There's a use of space wherein you're actually remembering something that's relevant to a different part of the computation, but that you don't need at the moment. And then there's the use of space, which is it gives me my inputs, and I look at it and I compute my output, and I store that in space. So how could you even hope to formulate a statement that captures these 2 uses of space? And the proof we're going to do is following the follow-up work of Benner and Cleve, which I'll actually state later and why it's relevant. But it's going to be the following recursive statement. So suppose I have some memory. So there's going to be, say, 1-bit memory, and there's going to be 3 of them. So R1, R2, and R3. This is just representing my 3-bit memory. Each of these holds a value. And in particular, let's assume they already hold some bit of memory. So this memory is in state tau1, tau2, tau3 in 0, 1, 2. Oh, wait, I'm not doing this. Okay. So
just use the rest of the board.
I suppose I will. All right, so I have this 3-bit memory that's already initialized to something. Okay, I'm at some gate in the circuit, so I'm at gate G, and I need the inputs to the gate. I've got G1 coming from the left and G2 coming from the right. So, furthermore, I'm just going to move over here. Yeah.
You can just use the entire, just ignore that line there. You can erase that line.
Oh, it's fine. I'll stick it in there. Maybe I'll do the proof there or something, but for now. So, furthermore, suppose I have programs P1 and P2. And what do they do? if I execute the program PI for I equals 1 or 2, the net result, actually let's call it PIJ. PIJ takes the J bit of memory and it adds the value of the ith child, either 1 or 2, to it. And I'm doing addition mod 2.
So this PI might depend on some input X, which you are.
Yeah. So we're thinking about being at a gate in the circuit, G, which takes as inputs G1 and G2. And I'm going to inductively assume that I have access to programs relating to the children. And the programs, again, what they do, I specify which of the children I want and which register I want to store it in. And it's going to add that value, mod 2, to the register. And for all other registers, it's just going to leave it untouched. All right?
It's RJ prime.
Yeah, urgent. So this is going to be the kind of recursion that I want. I'm going to add my input mod 2. So I'm going to pretend I'm storing some memory that's very relevant, tau 1, tau 2, tau 3 in my memory, but I don't know what it is, and I don't want to know. I'm just going to treat it as arbitrary memory, and all I want to do is have access to the things below me in this recursive sense. And in a recursive sense that I can get rid of, right? If I run this program twice, I get back to the memory that I had before. And I'm going to use this to compute my gate G in the same way. Then there exists a program PG of J, again for all J, such that PG of J's operation adds the output of the gate that I care about, while leaving the other memory unchanged. All right. So first of all, if this is true for every gate in the circuit, then quite obviously, this is enough to compute my NC1 circuit using only 3 bits of memory. Because just start with the all zero, your memory in the blank state, all zeros, apply this theorem to the output gate, and it just adds the value of the output to, I don't know, R1. And I just read the values right. So hopefully that's obvious, and hopefully it's also, again, intuitively obvious why this is a kind of useful primitive to have, because somehow, if I'm at a window where I'm trying to compute this node PG, or when I'm trying to compute G, I'm trying to implement PG, every time I want to call one of these programs, it doesn't matter what memory state I'm in, it doesn't matter if I've been altering the memory as a result of running this function. That now becomes the new tau 1, tau 2, tau 3 that I feed into this PI program, and it does everything it wants, adds the value of the gate that I actually care about, leaves everything as it was, and now I can just continue as if nothing had ever happened, now that I've popped back up to this level of the recursion. And again, I want to stress that this is disambiguating these two uses of space. The towers are representing all this memory that I care about from everywhere in the circuit. I might be remembering a little bit from here, a little bit from here, the full value here, all of it XORed together. But I'm just going to treat that as storage, and over top of it, I'm going to use space as memory. This is what's going to allow me to do this variance. So for this, I guess I probably will move to this side of the line. I'll leave this for the moment. Let's prove it. Base case. My gate is just equal to an input variable. Well, this one's simple enough. I can read the input. Those are different J's. All right, and of course, this can be an input level.
So these are the basic instructions of your program.
Yeah, the basic instructions of my program are all gonna look like this. I haven't told you what they look like, but intuitively, if I want to be able to use memory and then recover it, all of it is gonna look like I take something and I XOR it to a bit of memory. And the stuff that I XOR can't depend on this. Like if I do RJ is, I XOR it with something that depends on RJ, I probably have no hope of getting our memory back. So all of it are going to be these nice arithmetic instructions where I add to a bit of memory, something that depends on the rest of my memory. All right, good. I can use De Morgan's laws to only deal with NOT and AND gates, so let's just do that. So first, let's deal with the case of a gate is equal to the NOT of a gate 11. So it's not H. All right. I'll give you access to P sub H, J, and I want you to assign P sub G of J. So how do I do it? It's like 2 lines. Anyone who hasn't heard papers on this? Yeah, exactly. So P of G of J is as follows. First, you execute P of H on J, and second, you just take RJ and you add 1. Okay. This adds H and this adds 1, so you get 9. That's it. All right, cool. We haven't even used 3 bits of memory so far. Maybe we can take this down. Now, obviously, multiplication is going to be minimum. So the AND function. And the AND function is where it's like completely inobvious this should work, but if I tell you it works, you can sit down and you can think about it for a little bit and you'll get it. But we'll do it together and I'll try and give intuition as possible. So now, so I have to be clear by the fact that I'm XORing everything. I'm kind of thinking of all this being over F2. So really, let me write plus to me plus mod 2, and let me write times to me times mod 2. So I'm trying to compute G1 times 2. We're all okay with that? Okay. All right, so what can you do? Well, we've got 3 registers. I'm only going to prove, I'm going to do a PG of 0. Minus 3. Yeah, so I did 1, 2, 3. You can get all the rest of them by just like changing the value of the registers. So I'm just going to do this one to make it clear what's going on. All right, well, I have 2 other registers and I need to get the product. So I'm going to do the obvious thing. Going to store the left child G1 in register 1. Going to store the right child G2 in register 2, and I'll multiply them together. So what happens? At this point, my memory is equal to tau 3 plus the product of tau 1 plus G1 times tau 2 plus G2. And I'm going to get the term that I want plus all the cross terms. This is what I want, tau 3 plus G1, G2. And then I'm going to get plus tau 1, tau 2 plus tau 1, G2 plus G1, tau 2.
What you're saying is that if at the beginning, all 3 registers have tau 1, tau 2, tau 3.
Yep.
After I run these 2 programs plus this next instruction, now R3 has that value.
Right. And R1 has tau 1 plus G1 and R2 has tau 2 plus G2. All right. So this is what I want. Here are the cross terms. How are we going to get rid of them? Well, it seems pretty obvious, right? I'll run, say, PG1 on the first register again. So now I have tau 1 plus G1, so I'm back to tau 1. And now if I do once again R3 plus is equal to R1 times R2, what am I going to add? this adds tau 1 times tau 2 plus G2 to my memory. And this thing is just gonna get rid of this term and this term. Now I'm gonna do the same thing with the PG2 if I remember it up here. So now if I do it, if I put G1 back into R1 and take G2 out of R2, then I multiply them together, I get rid of this term, and I actually get an extra tau 1, tau 2 term. Finally, I load all of the G's out of R1 and R2, multiply them together, get rid of the cross term, and I reset the first and second
So
register.
I think it, what did you do in the second? Can you write it?
PG2, 2, and I execute PG1 of 1 again. So this takes G2 out of R2. This one puts G1 back into R1. And then I do the exact same instruction. R3 plus is equal to R1 times R2. That gets, so then you get plus tau 1 plus G1 times tau 2. And that's what's gonna get rid of this G1 tau 2 cross term, but now we're gonna get an extra tau 1 tau 2. This is easy enough to take care of. Just run PG2. No, it's PG1 because R1 has tau 1 plus G1, but R2 is back to its original. So I run this again and I do the same instruction here one last time. This gets rid of the this just activates tau 1 2. So yeah, it's a little bit of a hack arithmetic. This is an inefficient way of doing it. You can pretty clearly see if you rearrange the recursive call, since all I want to do is add each term once, you can get this down to like only pulling it 4 times. But who cares? 4, I think I ended up with 6. Yeah. So. Good. So that's it. The other interesting thing to note is that this thing takes 6 recursive calls. These ones each take 1, or 1 in the not case and 0 in this case. So what's the total number of instructions that I need to compute this whole thing? Well, at every node of height h, I need to make 6 calls potentially to h minus 1. The total runtime of this thing is like 6 to the h, where h is the total height of the circuit. We have a log depth circuit, it's an NC1. This whole thing takes polynomial. So yeah, in polynomial time with 3 bits of memory, you can do any formula of logarithmic depth, which actually means any formula that you can always balance. So yeah, that's a lying version of Cook and Mertz.
Let's follow. Now we remove.
Fair enough.
We follow lines.
Yeah, like the fact that multiplication works again isn't obvious. This is the only way I can come up with, which is just like, once you have the term you want, canceling out the lower cross terms, you just figure it out. Again, there are more efficient ways of doing it, there are other ways of seeing it. This is, I think, like the easiest way to think about it if you want to reframe it. Just
Question is these all the functions that you need. So it's getting the lots on the.
yeah, you can use De Morgan's laws to switch the ors to ands using the not ands.
Assuming that if I make or so set of populations that cannot.
Yeah. Sorry, NC1 is defined as and or not only on pan and two. Yeah. So I switch it to and not. But you can think in this framework, there are other, if you throw other functions into the mix, it's possible that you can do that. And in fact, this approach I said comes from a result of that and leave, so I just want to mention that that's the follower. I think the original publication was 87. This one, or maybe 80s. So they said the same thing, but they said it about a different model called sharp NC. And now instead of 3 bits of memory, it's 3 what they call registers. So registers are exactly these things, and what's sharp NC1? Think of it as the exact same thing as NC1, but now it's arithmetic operations. So there's some underlying field, so there's some set of values it can take, and you have a circuit of logarithmic depth that supports fan into plus n times over that field. And what they claim is that basically the same thing works if you're allowed to have 3 blocks of memory, each of which saves 1 field element. You can implement the whole thing. And in fact, it takes almost no additional work here because I already took care of inputs and the times operation. All you have to do is the plus operation, and the plus is basically as easy as not H. So I'm even going to write here. If you want to do G1 plus G2 over the field, all you have to do is run PG1, and then you run PG2, both on the same memory. And this one adds G1, this one adds G2, and you're done.
I have a question.
Yeah.
It may be stupid, but I mean, I see we didn't show that 3 bits is tight.
Oh, 3 bits is tight. So no, so Barrington's theorem actually is not phrased in terms of memory. It's phrased in terms of branching program width. And 3 bits translates to width 8, because again it's exponential. He gets width 5. So it's like log base 2 or 5 many bits. For whatever that means. And that is essentially tight. Yeah, Barrington's theorem came out of the line of work where people were trying to show no constant width branching program can compute NC1. Constant width permutation branching program, sorry, I should be specific. We don't have to get into that details. 2 is trivial, all you can basically do is compute like the XOR function. 3 is, they also have control over what that means. 4 is a little bit up in the air, but I think you can show it can't get NC1, I forget. But 5, you get it. And it's not quite this proof. There's like unsolvability of permutation groups that appears. So it's like there's an S5 version of this going on. I do not want to get into that. So this is the proof that came up with better leave later. And again, if you don't care about the difference between 5 and 8, their result exactly recovers Barrington's theorem with this little bit of loss factor. But the point here is that this is truly an interesting result because these fields now no longer take 1 bit. They can have something like, let's say, logarithmic number bits, log n bits. Now, what happens if you apply the pebbling algorithm there? Well, if I have to remember log n bits at each level, this is like a log squared n space. But what they showed is that you can actually get this whole class into log space. And now, yeah, using the extra memory to like, for the uniformity of these instructions, to keep track of how long you've been running, etc. All of that happens in log space. But the important part, remembering everything that's going on in the circuit, gets folded into log space as well, and that's really their big contribution. I should also mention that's why it's important that this happens in polynomial time, is you need to keep track of how long you've been running, so you need to, account for it. Yeah, so this was a very quick overview. Hopefully, you can the important, the cool nugget, which is that you can get around the pebbling algorithm in like the very strong sense by getting around this direct sum thing, which is that the space that you have to store things is not space wasted or space that you can't use for other purposes. That's like the important part of this whole setup. And are there any questions? Or there's like one more topic I want to talk about before the break. Or before we maybe take a quick break. That's permitted. I don't know. I've never given the seminar of champions before, so. Okay. Cool. So the last thing I want to talk about before the break, and in some sense why I'm here specifically, is this recent-ish innovation in space-bounding complexity, this alternate model, which is called catalytic computing. And this is where really this challenge to the direct sum of space comes to really start knocking on the door of this tree evaluation problem. Because this was defined after tree evaluation as, one of its main goals is to pose a challenge to this conception that extra space that's full is not useful. So catalytic computing was defined by Berman, Cleve, Law. No, Cook Law has been HRJKL, yeah, got it. So the setup sort of takes this, what we saw before, this tau1, tau2, tau3 thing, and it embraces it wholeheartedly. We could have tried to analyze what tau1, tau2, and tau3 were in that algorithm by way of the recursion, but we could also just say, look, whatever it is, I'm going to pretend it's completely irrelevant to my purposes. I have no control over it. A catalytic time machine is one where, just like in the classic setting, you have the input X written on some read-only tape. You have this little working memory of length S. You have, say, a 1-bit output tape. And now, the twist is that you have a new tape. Think of it as like exponential in the length of your work tape. This is like, this is log space, this is like polynomial space. This is a huge tape that is yours to use as you wish. It is a work tape for your consumption. The only problem is that it is initialized to some state tau, which is the memory in it when you start. And you're allowed to use it however you wish, but you must return tau to its original position at the end of the computation. All right?
So original position.
The original state. So tau that would be in the middle. So, and this has to work no matter what. So this definition is independent of tau, kind of like the lemma that we saw before. And I think at the beginning of their paper, they have this cute little parable where they say, so imagine, you've got your pathetical RAM there, and then you have your hard drive, and it's just sitting there, with like 15 pirated copies of Inception or whatever's on your hard drive. And like, you should be able to use it for computation, but you need to use it in such a way that you actually can, get it back at the end of the computation. You can't just erase things and use particular memories on it. So this was how they opened up the paper, but in reality, you can see that this is something that is useful for challenging this idea that you can't use full memory. And you can ask the question for various setting capacity. This doesn't have to be 2D as we policy, but think of it as like 2D plus. You can ask what additional power this gives. So I already erased our little diagram of complexity classes. I'm gonna kind of put it here again. So catalytic log space. Catalytic log space is the case where I set my tape to be a log, like a log space machine, and I'm going to give you access to a polynomial around this catalytic. And so the question is CL any more powerful than L? Can it do anything that L can? And the answer that they gave, they're too low. The answer that they gave is that you can get non-determinism and loop. So this class, CL, is by all beliefs strictly more powerful than log space, and for actually interesting problems. And how do they do it? Well, it's going to look a lot like the argument over there. So I may not run through it in all detail, but I want to just give the key point of it so that we're once again adjusting to this framework, because this is going to be what we're going to use in the second half of the talk, which is talking about the tree evaluation problem. So there's a class that I didn't draw on here that's wedged between NL and NC1, which is called TC1. And these are the threshold circuits. So before, in this NC1 model, all we had was this fan-in, 2, and 4. Or in the Sharp model, we have this plus and times. In TC1, I will allow you unbounded fan-in threshold gates. So AC1 is the class still above NL, where you have unbounded fan-in and some loops, already a generalization of the NC1 accelerator. And now we're going to generalize it further and say this depends on so I'll give you this very expressive gate class. And you can define it in a couple different ways: thresholds, majorities, etc. The gate we're going to use for today is I will give you what I call G equals L. And when a G equals L, says 1 if the sum of your of all the input bits. Sorry, I guess I should call these the GIs. These are the gates feeding into this. If this is equal to 0, no, sorry, is equal to exactly, there we go. So every gate in the circuit specifies the number, and all it asks is whether the number of incoming wires that hold 1 is exactly L. So you've got a circuit of logarithmic depth composed of these things for different values of L. And how do you show that it's an catalytic log space? It's a statement very much like before. So assume we have a program P, I'm gonna call it D minus 1. And what does it do? It takes some blocks of memory, Ri, and mod 2, it adds to them the values of the GIs. We can actually draw the circuit. This is G equals L. It's going to take an inputs G1, G2 up to G. So I have some program which simultaneously adds each of these values to their own little block of memory. That's going to be the recursion. And of course, what we show then is that there exists a program PD such that to some special memory recursion or 0, we add to this exactly the value of pair. The sum of the GIs is equal to L as an indicator.
And are you assuming there's a single program that does all the gates on the previous level?
Right. And so really what this program PD does, it actually does every gate at this level. This is the necessary recursive step. So actually, this is a good time to introduce the analysis that's involved in these things. So before we had fan-in 2. So what do we say? Well, we got a recursion program for G1, and we had a separate one for G2, and we wanted to come up with one for G. This program G used a constant number of calls to each of them. So it was a constant number of calls total. You have a log depth circuit. So the total runtime, this thing is like the number of total recursive calls to the level that you always make to a level below, right? To the total height of the circuit. So number of recursive calls to each. And that was good enough for our purposes. Constant, done. What happens if here, instead of having this group call, I just want a recursive call P1 that gives me G1, I've got P2 that gives me G2, I've got P3 that gives me G3. Well, just to get access to the input to GL, I'm gonna have to make like n recursive calls potentially. And now, if I have a log depth circuit, this thing goes to quasi-polynomial, and I have no hope of getting this in catalytic log space, so I can't even keep track of how long I've been running in the free memory. So they do something which is going to come up later, so it's good to have this digression. They show that their recursive statement is, well, I'll query the whole level below me, and from that, I'll get the whole level above me. I'm only going to show you how to get one gate. You can use your imagination to get all the gates in parallel. It's not particularly hard. And of course, the big thing here is that we're in catalytic log space. We have an enormous amount of free memory. I can have, polynomial number of bits for every gate in the circuit. And every point in time in the execution of my program. All of that is fine. Like I can have as much memory as I want. So making big statements like I can load all the memory into different spots is not going to be a problem for us. The dominating factor is whether or not we can get it down to a polynomial amount of time. Because the free memory is essentially going to be used for one purpose, and it's keeping track of how long we've been working. And okay, the circuit is uniform, so I have to compute the circuit. Oh, and I'll set aside 1 bit for the output, etc., etc. All the action is going to happen in the catalytic memory, and our only job is going to keep it down to a low number of recursive calls. Is that fair? All right, I'm not going to Trying to decide how much to go into this. I guess I'll say just a couple words about how this is done to demystify it. You can fill in the blanks for yourself. This program PD is going to be comprised of two parts. There's going to be a thing called psum, which takes a register R sum, and it adds to it the sum of the GIs. This program you can probably even come up with, it only takes a couple of lines, just, add all the stuff to its own registers, add that to R sum, take it out, subtract out the contribution of the terms. No problem. I'm switching between fields. I said these are bits earlier. You can think of them as actually being over a larger field. Again, plus, where I say plus, sometimes you need to do minus. This is a big issue. But in particular, let's pick a field like FPS. PS is the S prime. So it's a prime that's slightly bigger than S, where S is the number of gates I'm taking in. Clearly over this field, I can store the sum. Okay. That's the first part. And the second part is P caret. Actually, I'll just do P. So this says if I can recursively compute a value, which in this case would be the sum, then it's going to take the a certain power. Basically, I can do power. And the point is just that with Fermat's little theorem, this is enough, right? I take this sum, I subtract off the value L that I care about, I raise it to a power, I either get 1 or 0, and that basically tells me the answer to the thing. So I'm just going to say that this equals sum minus L to the power of PS minus 1. This one is less obvious.
You mean R sum?
Huh? Say it again?
You mean R sigma or?
Well, no, I'm going to assume that I have P sigma going into this recursive call, and I'm going to use it as a subroutine to store the power of it in some other register. Yeah, I mean, I have a bunch of memory. I can move these things around. So this thing can be done with a constant number of recursive calls. Again, add everything in, sum it all up, remove it, subtract off the contribution of the text. This one, the fact that you can power to an arbitrary or like linear power with a constant number of recursive calls, this is not so obvious. But I'm not going to talk about it. So read the paper if you want more. This BCKLS paper is actually a really nicely written paper, I must say. It has a lot of cool insights. So this proof is not very hard. It requires something about binomial coefficients, and then you're basically done. But suffice it to say, this is enough to express the power of CL. That's something that can be directed as connectivity. The determinant of matrices can be captured by this, and a number of other functions that we care about. I guess matching. We talked about this yesterday. Yeah, I guess matching can be done as a result, etc. So this catalytic framework clearly shows that we can do a lot with this memory that's full, and it was stated somewhere in the paper, I believe, that this is a challenge. This is at least a partial challenge to the idea that this tree evaluation should be exactly as hard as we think it is. And after we take a break, I'm going to talk about how in the last 2 years, this whole idea has been adapted to actually get better tree evaluation outcomes. So any questions for break? We'll see you in 5 minutes. We're good? Oh, cool. All right, so tree evaluation. How are we going to make this work for tree evaluation? So reminder, what's the object I'm working against? I'm working against an arbitrary node. So call this thing G and its inputs G1 and G2, just as I was before. And now I don't have plus times powering equals. I have an arbitrary thing here. Well, okay, first of all, this isn't even an arithmetic object, and everything I'm talking about so far is so okay, I managed to take the majority function and shove it into a purely arithmetic object. So why don't I do the same here? So first things first, I'm going to think of this as a polynomial. Right, what else can I? Well, what is this polynomial? Well, if I had to write it out explicitly. Okay, so as soon as I want to do this as a polynomial, I'm faced with a couple options. I could think of these elements as being elements of K, and now I have to do some work over the arithmetic, the field arithmetic, FK. Is K a prime? Is this going to work? What happens? I don't know. I don't actually want to do that. So I'm going to think of this as being log K binary bits, because that's something that's easy to reason about. So now everything's over F2, and that's fine. So really, for every output bit, I have log K output bits to compute, and for each of them, I can write the polynomial as the sum over all x, y, and z. And what do I want to say? Well, first, I want to check that the ith bit of xi is actually equal to 1. X is going to be like the output of the thing. Then I need to check that this polynomial f on inputs y and z actually outputs x. Y and z are going to be the values of my left and right child, respectively. G. I said G. Good. Great. What do I actually call this GL and GR? Okay. So now I checked that I want this thing to be equal to 1, so I checked that the output bit is the output bit for x is actually 1. I checked that y and z actually give me x when I plug it in, and finally, I checked that I actually get y and z from the children. So this is product over all bits I prime, and it's that y I prime equals GL I prime, and that I prime is equal to GR I prime.
Doesn't depend on other things.
Which other
time from
it just depends on the two children below. We've got a tree-like structure, GL and GR are the two things feeding into G. So this is like a big Huta, right? I just checked if the left child is what I want it to be, and the right child is what I want it to be.
So let me try, so this polynomial that you've written, TGI, is a polynomial in 2 log K variables.
Yeah, let me indicate those variables. This
Right.
and this are the variables.
Right.
Everything else, Z, X, Y, those I'm just summing them. These are all, in K. The only inputs here are G, L, I, and G. I guess if I'm writing this as P, I should really say. These are like the polynomials being computed in the lower logs, but okay, you get what I'm saying. These are the variables, and yeah, there's 2 log K, because I have to take the product from I from 1 to log K, and there's log K on the left side and log K on the right side. All right. I want to make a quick note here that we're already starting off on the right foot. And the reason why is because we have to deal with two restrictions in order to hope to get an upper bound. Read once and thrifty. Read once, very clearly this recursive structure of always calling the gates below and everything, many, many times. Read once is totally out the window. And furthermore, finally, the thrifty restriction is also gone. Because in order to compute this polynomial, I actually have to look at every single value in the gate G, regardless of whether or not it's actually relevant. So this is a good sign that this approach at least can work. Now, will it is a different question. I'm not going to, so this polynomial in the form that I said is, you can look at it in polynomial time, just, running over 3 elements, each of which can take a value up to, remember K was like N. This thing is just reading a bit of the, like a part of the input, I like go into the tree, the function truth table, and I read this thing. So, okay, this is like an object of small enough size. But now I have to actually compute this whole polynomial in this recursive structure that I had before. And remember the analysis from before, what do I actually need to get this thing into a reasonable space? Well, I need to be able to compute this and this only a constant number of times. I can only make a constant number of calls to the layer below me at any gate, because the height of this tree is like h, think of that as log n. It's the same setting as before. And what's my memory going to be? Well, I said that there's like log k bits here, log k bits here, and there's going to be log k of these things. So maybe we can get the same parameters as before. Maybe all we need is RG1 up to RG log k. Similarly for L. And similarly for R. Three log k bits of memory, that's totally tolerable, right? That's log space. These are going to be the registers over F2 that are going to try and do everything that you saw before with times and plus. I'm going to try and do it here. This would be a tolerable amount of memory, log k. And if I can get it down to a constant number of recursive calls on each side, then it's like 2 to the order h. Okay, so I need order h bits to write that down. 3 log k bits to write this down, h plus log k, that was my log space. All I have to do is compute an arbitrary polynomial with a constant number of recursive calls, which we're not going to accomplish. I think that should be pretty obvious, but we'll do as best we can.
So when you say constant number, you mean it's fine that you have log k different polynomials, each of them.
Yeah, so this is another thing. This is why it was nice to bring up the powering thing from earlier. I'm gonna have to design it such that I can compute all of the polynomials, 1 through log k, all in at the same time. I didn't actually go through that in the powering case, but it's just worth noting that like everything can happen in parallel. Like I can isolate everything to do with a single output gate of the D layer. I can just take all the memory and then it's taking from the same stuff in the D-1 layer at the inputs, but everything else happens separately. I had a catalytic log space, I had all the memory in the world to do that stuff. Here it's a bit trickier, you know, I only have 3 log k bits. I'm not going to use any memory except for this one, so I have to do everything with it. And that's going to be a point, a sticking point that's going to come up a little bit. But before any of that, like, what do I have to do here? Well, before anything else, I haven't even told you how to take like an unbounded can, right? Times of more than 2 things. Benner and Cleve had this very cute algorithm that got you times with only a constant number of recursive calls, but that makes sense. There's only a constant number of inputs. Now there's like 2 log k inputs, and it's not at all obvious how to proceed. So, what can you do? So I want to design this program for product. And again, assume I have this program, this global program, P, say I call it P below. Or actually, for the moment, I'm going to toss out the issue of efficiency, because our initial efficiency is going to be very, very bad. And I'm just going to assume that you get access to each input bit by way of its own recursive call. So I'm going to assume you have programs PI for each input bit I. And it adds the GI to RI. And now I want to give a program that takes the product of all these
Where
things.
I is something like L, I.
Well,
R,
ultimately it's going to be like 2 log k, but for now, let's step back a moment and just say the abstract challenge of computing an arbitrary polynomial. Okay. So I mean, ultimately, you don't even want necessarily the product of all the GIs. You want like them flipped by a certain amount, or you can expand this and consider every monomial separately. We'll deal with those issues if they come. For now, just give me a product. Just give me a way to compute product. So there's one obvious way to do it, concerning what we've already seen. And it's okay. I want to take the product of D things. Why don't I just take the product of adjacent 2 things, and adjacent products of those 2 things, and those 2 things, and all the way up. So yeah, option B. Then we're going to cleave on the tree. Good. What does that give me? Well, if I take a product of D things, let's say I'll write the D here so that it's on this. Well, efficiency parameters. This thing has height log D. Every gate has to make constant many calls to the layer below it. So it's a constant to the log D. This gets D. So order D recursion.
Oh, it's more like poly D squared.
Oh, yeah, sorry. Poly D recursion. Space is actually you can't do it quite with only this space because you need to save the intermediate things, but the total size of this tree is at most like 2D minus 1, so it's like order D space. And that's fine. I mean, you're gonna need D, I'm assuming you have D+1 registers just to store the inputs and the outputs. So order D is tolerable. All right, this is fine. Turns out this is a dead end, but we'll get to why. Option 2. Option 2 is also like a souped up version of better and bleed, but instead it takes a look at the structure of what we did before. So remember what we did before was like, I compute the top degree thing, top degree in terms of the inputs GI. And now I have all the stuff of degree 1 less that I have to cancel out. So I do it, I remove each of them in turn, and then I just compute that term. Then I compute the level below, whatever the coefficients are at the level below, and then I go down and down and down. And this gives rise to the following. Sorry, this is very hard. There was a point that I missed talking about earlier, so I'm just going to bring it up now that I've written this. When everything was binary, running PI twice, reset your memory. When you move to higher fields, you actually need to do inverses, which is instead of adding, you subtract. Well, every instruction was arithmetic, so really the way you get an inverse instruction is you replace every plus with a minus. Every regular program with an inverse program, every inverse program with a regular program, and you run the instructions backwards. And it's pretty trivial to see that like each instruction cancels out the forward instruction, so the net result is to subtract it. So nowhere in this am I going to discuss it, but as long as the instructions are all well behaved, I can always assume any forward program is accompanied by a reverse program. This is over F2, so I don't actually need that. It works, but I just wanted to mention it because we are going to deal with different fields a little bit. So don't worry about inverses. Okay, so I don't know if you can see this. What is the second line? What second line says I take R0, which is the target register of this thing. Maybe I'll call it R product. Oh, so I add to it some coefficient that depends only on the set that I'm taking times the product of all the RI registers. Yeah. So this is like when we had before, where the coefficients were all 1, right? I took the product of R1 and R2, and I did it over every subset, like every subset being when I load in the GIs into those tau i's, and I leave all the other ones as just tau. And again, the argument that I said before basically works. You just kind of induct starting, or you look starting from the top. You know, if I take the product of all of the tau I plus GIs, this gives me the product of all the GIs, which I want. Now, in order to get rid of the jump terms, I need to get rid of, each degree D-1 jump term. So I just set whatever the coefficient is, the minus of whatever's existing there. I do each of those. And notice I'll never accidentally reintroduce a jump term because you're kind of working your way monotonically down with the number of GIs you have loaded in it. So if I only ever look at when there's like D-2 GIs loaded in to the RIs, I'll never accidentally get a product of D-1 GIs because we just can't have that. Not that. So you just kind of work your way down. It turns out these coefficients are just like a plus minus one. And the order doesn't really matter, it's solid.
Sorry, the program is, it's like a for cycle and you run over every subset of D, right? Where D is the number of,
D is the number of things taking from.
of factors.
Yep,
And then for each such set, you first run PI,
yep,
which puts GI. So now after running PI, register RI has tau I plus GI.
yep. And every other RI that's not in the set has exactly 10.
That's exactly tau I.
Yes. Right, so that's like that.
Can you, so what's the, can you write down what's the value that's being added to our pi just there?
Well, the CS, you have to kind of calculate it and
Write it down. Well, let's figure out, let's just,
Yeah.
it's CS.
It's inclusion exclusion, so it should be what? So C of the full set.
No, we can figure out what C is.
Oh, sorry, C. C if this thing is 1, so I want 1 copy of G1 up to GB.
Sorry, what is that? That's like, that CS, whatever
Yeah.
that is.
See, this is just the coefficient that we're whose value we're working in.
Right.
And this is the product of all I, not just one of R.
Right, but when you write down with the tau i's and GI, so what is it actually? It's the product.
Yeah, this thing is just the CS times the product of all I in S of tau I plus GI
Right,
times the product of all I not in S of tau I.
so in this you're adding to our pi,
Our
pi.
yeah, so you just end up adding the sum over all S.
So in the end, our pi is what, tau pi, I guess?
It's tau pi plus the sum over all subsets, whatever the coefficient I said it to be is, times the product of all I in S of tau I plus GI, times the product of all I not in S of tau I.
Now the claim is that I can choose CS in such a way that this entire sum is exactly the product of the GI.
Yeah. Yes, that's good. And again, we can work out the value of the coefficients, but it's clear to say that they exist because you just work your way inductively down on the size of S. You pick C of the full set to be equal to 1. This gives you exactly 1 copy of the product of the GIs plus jump terms. Each of them has its own coefficient, happens to be 1 at the start. Now, to eliminate them, if I want to eliminate each term of degree, and degree I mean GI degree, D minus 1. Well, the CS corresponding to being minus 1, so I have to subtract those all out. Again, it's all over F2, but let's just do this in full generality. Minus 1 cancels out exactly those terms. It also subtracts out other jump terms of degree D minus 2 and below. And you have like D choices, so you subtract out a bunch of jump terms a bunch of times. And you add back in the jump terms for the original one of degree D. Doesn't matter, it's some number. I move to the set of size D minus 2. Whatever that number is, I put the minus of that, and that's my CS.
The point is that by symmetry, this number CS actually only depends on the size of it.
Yeah, it will. It only depends on the size of this. Yeah. It doesn't even really matter. I mean, in the non-uniform world, it doesn't even matter if there's symmetry or not. All you need to know is you don't reintroduce jump terms you already got rid of. And that one is just because you'll never get a higher degree G term if you limit the number of G's that are in the registers. Yeah. The lower degree G terms like go up and down, up, down, up, down, up, down, but eventually their turn comes and you exactly cancel them out and then you never revisit them.
Okay.
Yeah. Is that all right? By the way, these jump terms do turn out to be exactly minus 1 to the D minus something else.
And you will eliminate all of the jump terms.
Yes. Yeah.
By doing the same thing, but for a lower degree.
Exactly. Right.
And then when we reintroduce again, the terms that you reintroduce will be the degree less.
Yeah, you can only ever change the coefficient once, and S has come up. If you were
One coefficient, then the remaining coefficient will be also one degree.
exactly. You just work your way down, and in the end, you'll get exactly a 0 coefficient in front of everything except for this one GI that you left us.
Right, that works. It's terrible. It's 2 to the D of a
It is terrible. But it's what we got. And sometimes you don't complain about what you got. This is D times 2 times 2 to the D, roughly speaking, recursion. This D is eventually going to go away because these PIs are going to have a way of calling them the all at once, but it's still like dominated by 2 to the D. That's pretty bad. The space was just to say outright. This is I don't use any registers except for the RIs, and my target register are around. So perfect space usage. But this is awful. This level of recursion. In fact, what happens when you apply it to the tree evaluation problem? Well, the degree is going to be something like 2 log k. By the way, this is even assuming that I can, like, let's just assume every node only has one product. Forget the polynomial thing. Let's assume it's one product of degree 2 log k. Then the runtime is already like 2 to the 2 log k, all to the h, which is equal to k to the h. And if you take the log of this, this is the amount of space that it needs to keep track of how long you're running. This is h times log k. Sorry, there's an order here. And remember, this was exactly the conjectured lower bound by Cook and Mertz. So that's pretty unfortunate. Nevertheless, this was actually the starting point of our original paper, which came out in 2020. So this is everything I'm going to say in the back, but this lecture is going to work with James Cook, Steve Cook's son, who decided to make it his mission to disprove his dad's result. I should say that this Cook et al. Thing, this CMWBS, Steve Cook spent the last 10 years of his career working only on it, and he offered a $100 reward to anyone who could beat H log K by an asymptotic factor. Which is ironic because he's explained by his son and his master's student, both of whom have received much more than $50 each over the years in goods and services. So yes.
So why doesn't, because the other one would be where D is now like log K, right? So the other one would be
Yeah, the other one's really good. Okay, right. So let's say this.
there.
Okay, poly D, that's like poly log K. So this thing, actually the runtime, if I could use this is like this is like poly D or poly log K, the H. And that's like, if you take the log of this thing, this is order H times log K. So we've gone from log squared n to like log n log n. Very nice. That's using this average. Okay. Assuming everything is one product. And the trick is, of course, that we want to use arbitrary polynomials. What happens?
So option 1 has a problem. So option 2 doesn't have a problem for arbitrary polynomial, right? Because you could just in parallel do PI and then this R prime would be some polynomial.
I claim this algorithm, pretty much no change, works for this. And the way you do it is you replace this statement. So instead of CS times the product of all things, you do CS times the entire polynomial, e.g. I of all of your input registers, R at 1. Why? Because this is linear in all the terms. Just add this across all of the different monomials. Let's assume it's homogeneous. Let's assume that all the monomials have exactly the same degree, and that's going to be the degree that I fix here. So really now it's going to be overall subsets of the n variables. And I might have to adjust the coefficients a bit because some monomials might pop up a lot of times for the other ones that appear. But in fact, you can even assume, well, I mean, looking at this construction, I just assume every monomial includes exactly one copy of each of the variables. It's just, sometimes it's one minus that variable, and sometimes it's that. So if you just apply it directly to this definition, where these subsets are over all 2 log k variables, then this exactly, substituting this part into this works.
Does it depend on the term not RCS?
Say it again?
The term RCS doesn't depend on S.
Yeah, but neither does this expression. Product of I and D of Ri. The CS.
No, it will depend on S. The point is that this RL and our R,
Yeah.
for different S's, there will be either tau I, right? These registers will be either tau I or tau I plus GI.
Okay. Okay.
And depending on different S's, different of these registers will be tau I and different will be tau I.
Yeah, so. Let's say it this way. You run over all SL, SR, each of which is a subset of one. So for every, total, subsets of the left side and the right side. Now I'm going to inductively find a way to, inductively I'm going to assume I can compute all of these bits at the level below in one recursive call. And this can be done, I didn't say how to parallelize this one across multiple PGIs. It turns out that since you're just running the recursive call in the same instructions, here I can add the product to every output register that I care about. So it's really easy to compute not just one PGI, but all of them at the same time.
So as long as each bit of the output has the same recursive call structure, you can.
They're all coming from the same input bits. So computing one polynomial versus computing all of them takes the same number of recursive calls. Because in this instruction, I'm actually going to do PGI for all of the output bits, or maybe for all I in some special subset of the output bits. That's where I get exactly this recursive structure. So in other words, I'm going to assume that for every node, I can compute exactly the subset of the bits that I care about, the subset of its output bits. And using that, I'm just going to, sorry, this is R pi plus equal to, no, R pi is going to be RGI. There we go. RGI, I'm going to add the right coefficient times the entire polynomial applied to PL and PR. Again, running over all subsets. And I'm going to do this for all the i's that I want to compute at this level. And if you just unravel this thing and take this algorithm and apply it term by term, the cancellations will happen to each different monomial separately. And so what you'll be left with is exactly the monomials in terms of the input variables with no contributions to the types. It's not obvious, you'd have to work it out a little bit, but the point is this algorithm parallelizes across all the monomials. This one does not. And kind of the reason why is because you have to store intermediate products. And it's not clear how to combine intermediate products when you're storing all the intermediate products at the same place. Like, yeah, you can store these all with different memory for each monomial that you want to compute. But now you're talking about space that's linear in the amount of monomials. The number of monomials here is like k, you're dealing with memory bit like k. And remember, k is like n. So now forget log space, you're in like p space. So intuitively, that's why this algorithm is completely shot. Okay.
The complexity of the top one with the linearity of the bottom.
Yeah, so what you want, of course, ultimately what you want is a function of recursive calls. The space to be like D, and for it all to parallelize across every single monomial. And that's what you want. And this, again, this is a condition of, sorry, this is not on the screen.
No, it's there.
This condition of parallelizability, I don't have like a nice syntactic way to describe it. I just, I can just show you when something parallelizes and I can wave my hands about when it doesn't. But right, so unfortunately, what this means is that using this one, we can't get tree evaluation, at least not obviously. And this one we can, but as we said earlier, the amount of recursion is just completely untenable.
Oh no, it just gives you the same as the.
Well, it gives you the same as the pedaling out.
The pedaling out.
Okay, so I came up with a very complicated way to match the pedaling out. That's why we got into this. Because if you do the same algorithm but more complicated, they're gonna look favorably. Sorry to make spot see watching this right now. Okay, so I think if people are willing to spend a little bit of time, I'm just going to mention how this segued into our original results and what we got. It's not a long digression. The only reason I call it a digression is because when we move to the new result that's coming out pretty soon, we don't actually, this is like enough of a framework for us. But I think I still want to mention this because it's just, since it's digression, I'll go over here because it'll get released pretty quickly. So what's the deal? The deal is just that now we have two. Here I used D space, and I was okay with that. If D was like linear, or sorry, logarithmic, because I have 3 log k registers, and I tolerated that, and now my recursion's low. And the question is, okay, why don't I balance these things? What if I spend a little bit more space, then maybe I can get some better recursion? And an obvious way you can do this, albeit again not useful, is what's called the one-hot encoding. So I am assuming that my numbers are from 1 to k are all written in binary. What if I did a different encoding? What if instead of RL1 up to RL log k, and the same for R and whatnot, what if I actually had RG1 up to RGK, and similarly for L and R? And now what I'm going to do is, instead of storing the binary value of the left or right child, I'm going to have an indicator. So I want to add, if the value of the left child, GL, if this is equal to some value alpha in K, then what do I want to do? I want to do RL alpha plus is equal to 1. All right. That's the one-hot encoding. And why would I do this? Well, what the polynomial becomes very simple. PG alpha is just equal to the sum over all. Okay, well, now it's just y and z because alpha is actually the value I want. So it's g of y z equals alpha times. Well, I guess it's P L Y times P R Z. So it's degree 2 polynomial. This is just 1 bit and 1 bit. Right? And so if I just apply option 2, which seems like the worst possible algorithm, my recursion actually instantly becomes perfect. I only need a constant number of recursive calls. Great. So, yeah. So it's 2 to the order h recursion. And all I had to pay to do it was that my space became now 3k registers, where originally it was 3 log k. And as I said before, k is like n, so this is a linear amount of space. So this is completely shot. But now we have 2 extremes. You end up balancing them, of course. What we do is we do something called the D-hot encoding. And the D-hot encoding is just that you have a bunch of blocks, and for each of them you set 1 bit. There's going to be D blocks, and exactly how you set each of those is going to determine it. And I'll just do the statement here. So you're going to have D blocks of length. Let's call it B. I need to represent every element in K, so I need that B to the D. This thing is at least K, so I can represent every element. The degree of my polynomial is going to be exactly D, which means the amount of recursion is 2 to the D. So 2 to the DH is my length. What is the amount of space that I need? It's going to be 3 dB, because that's just the length of this encoding. So I'm going to take the log of this to say it. So I need, this is actually going to be 4 to the D. H. So it's going to be like order DH plus DB. Did I forget any terms? I think that's right. Respecting this equation, so this is going to be like D log B is at least log K. And what do you end up picking? You end up picking D equals log K over log H. B equals H. So log K over log H times log H at least log K. And this thing becomes log K over log H times H plus H times log K over log H. So this is exactly equal to H log K over log H. And that's our savings from the original one.
Save a little log there.
You save a little log. And you know what? This earned me $50. Yeah. Canadian, which was not worth the effort. No, but it was quite cool. So what is this in terms of real terms? I would have said H is like log n, log K is like log n, log H is like log n. So you get log n squared over log n.
Right.
Yeah, hold your applause.
And of course, the next conjecture is okay, so this, okay. You can shove, you can get rid of a little log, but obviously it's still based morally log squared.
I told this to Bruno, but when I gave this presentation at an event in science, Alan Gordon came up to me after and said, "Yeah, but you can always save a log." He was not impressed by this.
Right, very good.
Of course, now I'm going to talk about why you can save a lot more than. This is the story up until 2021, and now I'm going to mention in a couple lines.
But that was already interesting because that already told you that the pebbling.
Yeah,
was
so this
not
already
a great-
like beating it by a log factor. It's a modest improvement, but it really does shut down the pebbling algorithm as a conjectured lower. You can try and relax it, but it's not clear how you relax it to give it an interesting statement.
Any pebbling lower bound we expect it to be true, except for this log you can shade, right? You could say something like
You could say something like that. It would even be reasonable in some circles. But like,
But
this
now
is
it's
pretty cool, right?
But now it's about to be completely destroyed.
Yeah.
Right?
But also this means that like somehow you can beat pebbling on an arbitrary polynomial, which means an arbitrary function, right? Like composing arbitrary functions doesn't like the pebbling algorithm doesn't hold up. Like this is a pretty serious objection, right? I mean, it'd be different if I was holding much smaller values of the leaves. I was trying to do like a weaker pebbling algorithm. Like this is basically the most general sort of pebbling thing you could say, and it's just wrong. So it's pretty nice. Now option 3.
Okay, right.
So it turns out there is a parallelizing multiplication algorithm that works in a linear number of recursive calls. That is going to be the main takeaway here. The registers are going to increase in size, and it is going to mean that the amount of space that we store is no longer logarithmic, but the amount of space we're going to store and the amount of the log of the running time will both be log n times log n. So now, well, of course, you can always shave off a log factor. So like this is basically log space. The positive direction of Morgan sticker. This algorithm is not hard, but it needs a little bit of stuff. So let's have a number n, and I'll tell you what it is later. And I want to pick a field that supports two things. The first, that I want an inverse of this number n. And the second is that I want roots of unity. What's a root of unity? It's a value over the field that obeys two things. Omega m to the n is equal to 1. And 2, the sum of all j equals 0 to m minus 1 of omega m to the j is equal to 0. This is roots of unity. And in fact, I'm going to add a small thing to it. This is true even if these are all raised to a k, as long as m does not divide. So it's not that they're co-prime, it's as long as A is not a multiple of N, you're fine. This is all. If they're not co-prime, then you actually get like a bunch of, like the cycle happens faster and you get a bunch of zeros, but a bunch of zeros is still zero. These are the two properties of omega n that we need. And I'm going to need M inverse for a separate reason. But so let's imagine instead of working over a binary field, we're now working over a field, some size that supports these things. And in fact, I'll even say that you pick a field that's pretty close to it, say like 2 to the ceiling log m plus 4 or something. So there's like a field that supports both of these, that's of size roughly, it's like at most 2 m.
So, what is the root actually? Is it like?
What is the root? Oh, I guess most of them change.
X minus 1 or x plus 1 or what?
I don't think x plus 1.
I mean, these are polynomials, right? Somehow.
Yeah, right. This is like solvability of a polynomial. Yeah, I guess right. Like x plus 1 should do it because you have to get past degree.
Maybe x. Yeah, x or something.
X. Are you sure?
No, because no, I'm not sure. But
I think you want to run over. I don't know. This is a classical. This is classical.
yeah, you're right.
I mean, this is math, and I emphatically do not know. So I punched to the experts on this one. X plus 1? Yeah, maybe that's.
But it's nice. It would be nice to know because it's a polynomial, you can write it in.
Yeah.
Right. Just what is the root of unity?
Yeah.
In
So
the field.
So right, this is a prime power, which means you can write all the elements as being modulo what it's
X to the
this.
this minus 1.
Yeah, x to the m plus 1 minus 1. So you take this as a polynomial.
That's the irreducible one, and I take.
Yeah. And then you take everything up to degree this, and then you
Up to degree this minus 1, right? And
up
then
to this minus 1, right? And then you
that.
multiply elements together, then you take it modulo this polynomial.
Right.
So
Doesn't that taking one of this? Isn't that just if you have something, if you're multiplying stuff, and if you have something of that degree, well, it ends up being a minus 1, and if it's big enough, right? Of degree, ends up being a 1, and if it has this degree plus d, then it ends up being x to the d or something.
So whenever you see that term, you can look at it.
Yeah, you can switch.
well, yeah, I mean, but you need the nth degree. Oh, the nth degree, not the one. Oh, is it the? Oh, is that how it works? Okay, yeah, I believe you. So.
Oh, no, that's not negative.
That's the. Well, let's see here. Okay, let's do it the dog way. Let's say this was
I think not.
1. No, if this was 1, this would be x squared minus 1.
I think it's the log, right? Because
Right, x squared minus 1 doesn't have more than 2 elements, right? And that'd be like f2.
Yeah.
So it should be.
Yeah, the number of elements of small degree polynomials. Like,
Right, so if we make this 1 again, and this should be 1, so then it's x minus 1, and you take all the polynomials of degree less than 1, modulo this thing,
so you have 0
and so you have 0. Oh, yeah, but
I
it's
didn't
over,
get it.
right, this is like over f2.
I-
Yeah, the field comes in, right, like, it's like, you do the modulus.
Yeah, but okay, so we don't know exactly what the root, but it's probably not very complicated. You figure out, did you just figure out or did
No. James and I figured it out at some point,
So you can probably write down explicitly the root and you compute and you just check that those two equations hold. I mean, it's probably, it's just some polynomial with those degree, up to that degree. Over F2.
Do we just want to bash this out at the end of the talk? Or do you? What?
There is no end to the dot.
Well, that's what I'm saying. Should we define this as the end of the talk? I don't know how I'm gonna stay here. Well, like I said, I'll give you a hard problem to look at while you're thinking about it. I'm gonna just come back to this later. I do want to give the punchline to this, before we
Yeah,
go.
all right.
So the punchline is actually really simple. The punchline is the fact that, what happens if I take the product of all I in, D of omega m j, sum of j equals 0 to m minus 1. How I plus this. So this is going to be my statement. And I want to figure out what this is. Well, this is going to be equal to,
Oh,
yeah.
what's the relevance of that?
Huh?
What's the relevance of this problem?
Well, you're about to see it.
Oh, you like.
Wait, but by xi there, we used to write it gi.
Oh, GI.
So you.
I switch notation every time I get the talk.
Yeah.
Just keep people on their toes.
So you want, in the end, we want the product of the GI, right?
Yeah. So I believe that this thing is actually going to give me the product of the GIs. If I pick n correct, there's gonna, yeah, and you'll see why. So the point is, let's take the sum of j 0 to n minus 1, that's on the outside. Then I'm gonna take a sum of all the degree terms in. So it's k equals 1 to the degree. Or I guess 0 to the degree. And for each of these, I'm going to end up with an omega m to the j k times the sum over all sets of exactly that size, k. And I'm going to write it, just to save some space, I'm going to write it as tau to the s, g to the naught s. This meaning the product of all I and s of tau I, this being the product of all I, not an s of gi.
Oh, it's modest.
Yeah. So you're going to get omega. You're going to get an omega k contribution because you're taking k tau i's, and each of them has a j term here. So that's the expression. And this thing, well, let's take the degree 0 term out. Degree 0 term is k is 0, so you get a 0 here. So you end up getting, well, let's do, I guess I'll just switch the sums first. Sum j equals 0 to m minus 1 of omega m j k. Sum of size of s equals k tau s g of s. And when s is 0, then all of these are 1, and so you get m of them. So this is equal to m times g with the full set, because it's not the empty set. So this is the product of all the GIs, plus sum k equals 1 to d, sum j equals 0 to n minus 1. You see where this is going.
Wait, no, just to take it easy. Sorry, now there is the j.
At this point, I'm going to set m to be strictly greater than d.
Right, so it means that.
Okay, so this is the same line as this one, but I pulled out the k equals 0 there. Yeah.
And now the point is that it doesn't actually depend, the sum of rest doesn't actually depend on j.
Yeah, so let me write the k equals 0 term here, so it's clear what happens. Yeah, so this is the sum from j equals 0 to m minus 1, omega to the 0 times j, times the product of all the GIs, because the k equals 0 term is exactly tau, no taus, all g's. This thing, of course, is going to be equal to 1, so you end up with just n of these.
Well, not this thing, the sum of those things. Right? Is it? Yeah, sorry.
The sum of those.
The sum of those things.
And for all of these, k is going to be between 1 and d, and I'm going to pick n to be strictly greater than d. And when that happens, I'm going to appeal to number 2.
Yeah, again, because that factor that has the sum over all s's actually doesn't depend on j. So you can just group.
It doesn't matter what's happening in the parentheses here, This is just some fixed value for each k, this is the fixed value
Times that sum
times this sum. And this sum
is 0.
is 0. Okay, of course, I need to get rid of the n that you get here, so I needed an n inverse. But this gives me my multiplication algorithm, which I'll just write out for posterity's sake. For j equals 0 up to n minus 1, I'm going to do r I times is equal to omega m for all I. You're going to run pi for all I. You're going to do R0 is equal to, okay, the outer sum is going to be taken care of by the loop, so you just take the product of all I and d Ri. And then pi inverse for all. I didn't say omega the j here because each time you run it, it's going to multiply by u, so you're going to inherently cover all the j's. Exactly.
You first multiply omega in Ri, and now it is Ri times omega to the.
I guess we'll write this as one j from one of the n, so it's clear that's omega to the j. But of course, when you reach j equals n, it's the 0 term.
So can you maybe use a different color and write? Okay. So we need just after the first instruction, you have omega n. After the first instruction, the value of Ri is omega n tau I.
So going into the loop at every step, you're going to have Ri equals omega n to the j minus 1.
That's before
Times
the loop.
our.
That's before the loop starts. Yes.
Now you multiply by omega m, and you get omega m to the j times time. Then you add this the x the g, so you get omega n to the j tau I plus x I, which is exactly what I needed for the polynomial there. Then I add R0. R0, of course, at this point has the sum of called j prime equals 0 to j of product of I and d. Omega j prime tau I plus xi. And then when I invert it, I get back to exactly where I started. Omega m to the j times tau.
No, yes.
Yes. And then you go into the next one. Clear? And
We get exactly after that. You get exactly that.
yep, the number of recursive calls is 2n.
I have that for 2D in the previous notation.
2n because I'm
No, sorry about
yeah. So moving over it is m,
2N.
but m again takes to be just slightly bigger than d. Pick m to be like d plus 1,
You're good.
and pick the field to be like at most 2n.
I see. So it's order D.
Yes. So it's already
Order D.
yeah. So what's the analysis of this thing? It's the number of recursive calls is equal to order d. But now my memory, well, I have 3 log k registers like before. Sorry, I flipped and now I'm just saying. Oh. One last thing. This works again in parallel over all the monomials. So instead of having this one product here, I put the entire polynomial as before. Every monomial, you will do exactly this sum, and now it doesn't even matter if it's homogeneous or not. Each monomial has degree at most m minus 1. So all of them are going to get the exact same cancellation. I never have to look inside the polynomial. I can just apply it in the dumb form that I wrote here without doing any expansion or anything. And I apply it as such. Again, I'm assuming I can compute the whole left side. Now I don't even need subsets or anything. I can compute the whole left side in one recursive call and the whole right side in one recursive call. So now this is Li and Ri. So I do this instruction for all of my input registers. I run PL and PR. I run my polynomial PVI on L and R. And then I do PL inverse and PR inverse. Now, by the way, remember the inverse actually matters a little bit here because I'm no longer over it. So I need to subtract over and add. This is a non-issue. This program with this replaced by a minus sign computes the minus of GI. So it doesn't matter. First of all, order D, memory, 3 log K registers, each of them is now over a field, which I can represent with log the size of the field. Log, and I had to pick something slightly bigger than M, like 2M, M is slightly bigger than D, the whole thing's order D. Log order D. And what's D? D is log K. So the number of recursive calls is log K at every level. The memory is 3 log K log K. And as a result, I get memory, which is H log K. Remember, the amount of recursion at each level to the H, and then you take the log of that. So you end up with H log the number of recursive calls. H log K plus log K. Log K. And this is an log and log n. Pretty much in its entirety. Any questions? Besides the exact value of omega sub n. The talk isn't nearing its conclusion yet, so we'll do this later. Well, I say that, but actually it is nearing its conclusion. Because there's not that much more I want to mention. Say it again? Oh yeah, right. So that's one of the things I want to mention. There's like 2 things I want to mention. But I'll take your questions. This is basically the end of the technical component, and also the end of the part that I really care that you remember. All right. So then let me just say a couple last things. Hey, remember the KRW conjecture from like 3 hours ago? Okay, so the KRW conjecture stated that this other version of the problem, where you have unbounded fan-in and k is equal to 2, this is an NC2. Do our algorithms apply to the unbounded fan-in case? Well, what is the polynomial degree now? The polynomial degree, let's say I'm now dealing with the tree evaluation problem, and I'm going to generalize all the parameters. I have k, d, h. Ooh, those are the same D. Let's make this delta. Okay. Fan-in is delta at every node. Elements are K. What's the amount of recursion I need? Well, the degree of my polynomial is now whatever it was before, it was log K.
Right, so the multiplexer relation is TP2.
Yeah, the multiplexer
log
relation
n,
I said this week 2. And then
2 log n.
Yeah.
Log n.
yeah. So before we had 2 log K inputs at each node, now we have delta log K. So that's the degree of our polynomial, which means we have to make the field size to be slightly larger than this thing, and the number of recursive calls is going to be slightly larger than this thing. Pretty much none of the rest of the argument is unchanged. So you apply that, and you get that the recursion is, well, this is the number of recursive calls in each layer, roughly speaking, take the log of it. So you get H times log delta log. And the size, well, now I can't save 3 log K registers anymore. I just save delta plus 1. Delta for each of the inputs and 1 for the output. So it's actually delta times log K times the delta field, which is log delta log K. There's an order in both of these, but that doesn't matter.
If for instance.
Yeah.
Yeah, let's do that.
Good. So you put these 2 together and you get the space usage. How does that compare to what we actually want? The size in TP is K to the delta times delta to the H. Delta to the H is the number of nodes in the tree, K to the delta is the amount of space you need, roughly speaking, to store each tree, log. Delta, K to the delta log K is how much you need to specify each internal node. Okay, so the log of this thing is H log delta plus delta log K. And if you just look at this, well, it's still, this log delta on the inside doesn't really matter. This thing is essentially log n inside the parentheses. H log, yeah, so it's even a little bit better. It's like H times log n plus delta log K times log n. So it's still a log n times log n. It's like you get all of this times log delta log K. Is my space usage, roughly speaking. It's actually a little bit better than that, but let's just say that. Okay. So our algorithm still works in log space if you do the fully general version. But assuming the KRW conjecture, this thing isn't an NC1. This was originally a way to try and separate NC1 from P, and now we've shown something much stronger, which is
NC1 from NC2, right?
yeah, this is NC2, but like no one really cared about NC2. Yeah, it's like it shows a sharper separation than P, but like no one thought that it was an NL or L. So as far as separations goes, it's like there's something here. Now it shows that the KRW conjecture implies that formulas are not the same as branching derivatives. That space and formula depth are separate. And this works even if you don't make any improvements to our algorithm, because you just take a pattern. The KRW conjecture implies that it takes formula depth roughly log squared n, maybe over log n. And this thing is in space log n times log n. So if I pad out the length by to like n to the log n, the problem's now in log space, and you only lose a log n factor in the depth of the formula. So you get a super polynomial separation between space and, well, branching program size and points. Or super logarithmic separation between depth. Space. That's nice.
So if you want to prove the KRW conjecture.
Yes, Bruno's favorite part about this is that if you want to prove the KRW conjecture, you should stop focusing on tree evaluation and start working on NC connectivity. Since the padded versions in log space anyway, since the padded versions in log space anyway, just take the log space complete problem and forget all this other crap. The jury's still out. The KRW conjecture actually says something kind of nice. It's like fine-grained. It says really that a composition theorem for depth holds. So you only have to prove like 2 layers, and then you get the rest. It's all well and good. But it is kind of cool that now, if you're gonna show that this problem's hard, you may as well show the estimate. That's nice. The other thing I want to say is a little bit more technical. So in between these two tree evaluation works, James and I had another paper, and it was about what we call universal branching programs. So the idea is you want a branching program that can compute any function. And there's this thing called a catalytic branching program, which is just like the non-uniform version of catalytic space that we had before. What is it? Instead of a branching program with 1 start node and 2 end nodes, you have a branching program with a bunch of start nodes and 2 times that many end nodes. And these each have a label, call it I, and these each have a label which says which start node would be better to come from and what the answer to the function is. And it works in exactly the way you think. If you start at any node, you will reach, when you run the function, you reach the node labeled with the correct start node and the output function. This also coincides naturally with the notion of amortized branching programs, because the idea is like you have a branching program size, the best branching program size for your function. Maybe if you blow it up to this size, if the branching program complexity was S before, as long as you can get much less than S times the number of nodes M, you've shown like amortized savings. Like computing many copies of the function allows you to save on this. Well, it's really the same copy of the function. Don't worry about it. So this is a model that was introduced by ToC and Mackenzie. And they asked the question, what's the best you can get? And Aaron Session showed that you can actually, for n equals 2 to the 2 to the n, you can get the size, you can get a program of size n times n. In other words, the average size is only linear, no matter what the function is. Very cool. So amortized complexity is trivial, essentially, for every function. This fits in with a long line of work of showing these like formal complexity measures when you go off to the like highest amortized setting. In fact, a couple years later, Robert and Zidane showed something similar, just using LP duality. And they improved on this M a little bit. And then James and I improved on this M a little bit as well. The way that we improved on this M is we basically took our for all S algorithm that you saw before, the way of computing catalytic products. We just treat this whole thing as a giant polynomial and we apply that. But to get good space instead of good time, what we did is we stored every binomial. So we said something along the lines of like for all S, you do PI as we did before for all I. And then you have a register for every possible subset, and you actually just add so you like saved the portion that had the GIs for later, and then when all was said and done, after the loop was over, only then did you add the whole polynomial. So if for one product, it would be like RS times the product of all I not in S of R. Sorry, this is PI inverse here. So this is the same algorithm as before. Oh, sorry. Why would this save any time? It's because you don't do this. You do this for all I and n once, and then you do this saving for all S. There we go. Sorry about that. So you get all of the VIs, then you save the like tau I plus or GIs. You save all the tau I plus GI components for later, and then you just when you're back to only having tau i's and RIs, you multiply the appropriate side of each one. And this gives you the product the same way that the old one gives the product. You have to get rid of the contribution of the tau s's, but fine. This is essentially what we did. So in other words, there's like a time efficient space inefficient version, and there's a time inefficient space efficient version of our previous one. If you just throw that at this, you get exactly back this result. And once again, if you balance the degree by computing only subsets up to a certain size and then using degree 2 or like unbounded Fanning degree products on that thing, you end up actually getting like 2 to the 2 to the epsilon n, and this is like 2 to the 1 over epsilon times n is the runtime. Where you basically pick up to you compute all subsets up to size epsilon n. Like this is exactly what we get. None of that's important because we now have this new algorithm. What happens if you apply it here? Well, it's a one-shot algorithm. There's no recursive structure anymore. The number of calls that you make, and now calls is just accessing the input, is like n. But to the n, because you have to n squared, because you make n recursive calls where each of them spends n time. So you query all of the bits, and then you do that n times in our loop of size n. And the amount of memory that you need, well, you have n registers, and they used to be Boolean because they used to each hold an xi. Now they are over a field of size 1 to the n, so you get like order n log n. And so that takes us down to n log n, but at the cost of making this thing n squared. So you get nearly optimal width and pretty close to the right length. Turns out you can actually get rid of the log n term by doing some tricks on this thing, which you can actually do in the original D7 as well. Tree evaluation. Yeah. You can save the log n factor on the width. You can't save it on both the width and the length. yet. So you still get an n, log n times log n algorithm. But essentially, you're embedding binary elements into a field of size log n. Why not just represent your elements over k using log n bits that can range over a range log n, roughly speaking. And you have to do some balancing or whatever, but when you blow up the representation, you end up eliminating the log n factor. I can show the details, but I think this is like going way too far afield of what's actually interesting about this work. So I just want to mention that now you can get the optimal width branching program for any function of length nearly linear. Now, this is worth thinking about as a subroutine. So let's say you have a branching program and you're trying to compute some global function, and to do it, you want to compute some subfunction, and you're at some width of the branching program. What this is saying is that without doing anything else, you could just compute that subfunction in basically like quadratic length without increasing the width of the program at all. So this is like a very useful subroutine to have because it doesn't matter what your subroutine is. All you need is that the subroutine is on at most like log n bits, roughly speaking. As long as you're computing some subroutine that's only like logarithmically scaled down, you can do it with no increase as many times as you want. So that's where these kind of universal or amortized branching programs, I think, will see a lot more interest. I haven't been able to find a good use for this subroutine yet. This is not so much my area of expertise, but this is something that I think people really care about. And I'll also note that we can't get less than 2 to the n as the counting argument, right? Like amortized though they are, these are still branching programs. So if you got to like 2 to the n over n squared or something, well, I guess it'd be n to the 4th, then the counting argument kicks in and you don't even have enough of those branching programs to compute every function. So this is roughly speaking the limit of the technique. There are other potential applications of our work to stuff about catalytic computing and whatnot, but for now, the main takeaway is that we're like hairs away from putting this. And as a result, we might be able to get some really fine separations and see some very cool things about things. So that's pretty much it. Thanks.
Cool, thank you.
I want to spend a bit of talking about. Discuss amongst yourselves. Any questions? Comments, concerns? Jokes? No. No, I would say that I'm just, this is all specialized in the free evaluation thing. Considering how general it is with all these polynomials, I'd really love to know more applications of this. So if you have any like space restricted questions that you've been thinking about and you want to see if this is applicable or you want to play with these models a bit, like come talk to me. I'm really interested in seeing where else this can go.